This one is compress.
Definitely not equilibrium.
No, this one is equilibrium. The location 2 is equilibrium. Location 3 is compress. So how many period?
What do you mean? Like the time from here.
No, no. How many period? Is it t? Is it period is?
I am pretty sure it's half t.
Half t is from here to here to here. This is half t.
Oh wait. It goes from compressed to uncompressed to compressed. Then it goes
No,
back.
It doesn't.
Yeah, of course. But a normal period is crest to crest.
Normal period is crest to crest.
Yeah, so that means this is half.
No, how this is half? Let me see.
This is.
Let me see.
This is half of the way.
Look. This is compressed to equilibrium.
Yeah.
Is T over.
Oh, I get it. Okay.
So, can you imagine a spring?
Yes.
Or spring.
Yes.
All right. When you see spring, whose name do you recall?
Hook.
Sir Isaac Newton. Are you crazy?
Hook.
When you see a spring, whose name do you recall?
Hook.
Sir Isaac Newton. When you see anything for that matter, whose name do you recall? When you see a light, whose name you recall?
Probably like Albert Einstein.
Sir Isaac Newton. When you see a Maxwell equation, whose name do you recall?
Maxwell.
Sir Isaac Newton.
Whoa, you're getting a special call from the United States President.
Oh, no, we're not going to take it. We have much more important. You remember Archimedes? Marcellus sent his people.
Mercedes?
No, not Marcellus. Marcellus, King Marcellus, sent his people to tell Archimedes to see him. And they came and said, "Hey, Archimedes, let's go. The king wants to see you." And you know what Archimedes said?
Do not disturb my circles. But anyway, are you going to get to the problem?
Yes. So imagine not circle. Imagine, when you see circle, whose name do you recall?
Probably, Euler.
Are you crazy? Sir Isaac Newton. Okay.
I mean Euclid, not Euler.
You can create a god from Sir Isaac Newton.
What?
From F equal ma. You're not gonna like everything I say, but this is not opinion. This is truth. Okay. Now let's go back to physics. A spring, right?
Mm-hmm.
If you put a spring and you drop a ball on the spring from like 55 centimeter above the ground, what happened? That's what we're going to explore. We're going to find the time, we're going to find the distance, we're going to find the velocity, we're going to find the acceleration, we're going to find everything.
Where's the smartboard pen?
I saw it over there.
Okay, so of course.
No, first I'm going to give you the problem. Hold on.
Can I clear the board and everything? Okay. Give me the problem and I'll write it down.
No. I have to draw it.
No,
baby.
Come on.
No. It's unique. Okay.
Okay.
Thank you. Okay. Let's see. All right. So draw a snapshot. Okay, one is spring, but snapshot to represent three scenarios. Okay. Here. Draw a line here.
So.
No, not that long. Okay.
So let's say this is at t equals 0, t1, and t2, right?
Yeah, t. Yeah, very nice.
Okay.
Nice. Okay.
And
I'll dictate. So draw a spring there.
Okay.
One second. I'm not ready. Okay. This spring at location 2.
Okay.
Same size. Size doesn't change. Okay, that's it. Now compress at location 3. Compress, much more compress. I want you to compress it much more. So erase it on the top.
Is it not noticeable?
It's not noticeable. For example, people who have, like my eyes, almost blind, not noticeable.
Okay, fine.
Okay.
That's almost half the length.
Now, can you put a x-axis Oh, before you put x-axis, can you put a ball 55 centimeter above the ground, above the top of the spring?
Okay, so that's 55.
Centimeter.
How long is this? How long is the spring? It rests.
Oh, I'm not gonna tell you.
So do we just not know?
We would. Can you put the ball, same ball, on the top of the spring?
Okay, so
Don't take up that much. It's sitting and not sitting. Okay, it's touching, not touching.
so it's just like just about to fall.
Yeah, so P is 0.
Yeah, and then here it's really pushing down.
Oh yeah, 100% compressed. Now can you put the x-axis?
Okay.
Different color, maybe red color. Put the x-axis. And move the x-axis by hand.
I don't have to. Well, do you want me to draw like?
No. Okay, no.
Well, what do I have to do?
Move the x-axis to all the way underneath when the velocity is okay, just right here. Put the x-axis right here. Oh no, it's not a straight line. It's cross the ball. It should not cross the ball.
Oh, you mean
top of the spring to top of the spring to.
Yeah, but obviously.
No, not like that. Can I draw this?
Oh, top of the spring to top of the spring.
No, the straight line, x-axis. Okay, this should be 55 centimeter from here to here, 15 centimeter from here to the spring.
Okay.
And that should be 0 centimeter from here to the spring. X-axis to the spring is 0 centimeter. X-axis, okay.
Yeah, and how much is this?
15 centimeter.
Oh, then you don't have to draw an x-axis. All you have to draw is a dotted line to show what.
We'll say no internet connection. Why no internet connection?
Let's just go to network settings. It sometimes freaks out. Yeah, there we go. It just didn't see this.
Password? Are you kidding me?
Well, we're not getting that right now. We'd have to look through our photos, but our phones are busy.
No. I'm gonna take the photos. I'm come back. You keep people busy. Keep talking.
Okay, great. So, can I still draw? Great, I can still draw. So, okay, here we go. So we have 15 centimeters, and I don't have the rest of the problem specified. But I'm guessing that this is the point where it's at 0 meters per second. So this is the max compression of the spring. So I guess our objective is to find the length of the spring. I'm not really sure. So obviously, the first thing we want to do is write down the energy. I mean, there's going to be the potential energy, the spring energy, and the kinetic energy. So at t equals, it's fine. No, I don't need it.
What?
It just allows me to keep working. So at time equals 0.
Oh no. Draw the table.
Oh yeah.
Draw the table. Okay, I'll give you the K.
Oh okay. What's the spring constant?
Mass is 2.6.
Okay, so the mass of the ball is 2.6 kilograms.
Yeah. I'll give you the K. 1585.
1,585, right?
Yeah. This is the K for which spring?
This spring.
Yeah. How many spring do you see?
There is one spring that we're picturing 3 times.
Right. So now.
All right, I can do.
No, I'm not. I didn't tell you what to do. Velocity. Can you write the velocity on the second one?
Okay. We'll find that.
Okay. So create a table over here.
Okay.
No. Create a table over there.
Okay. I'll do it. So t equals 0.
No.
Equals
Table.
Yeah. Give it 1 second.
No. Light location 1, 2, and 3 on the.
But
On the vertical line.
It's the same exact thing.
No. Give it to me. Give it to me.
No.
I have something on mind.
Oh, well, what are you doing?
Then just give it to me. Okay. So t B, B.
This is
A.
not a good way of.
This is 1. This is 2. This is 3.
This is a terrible way of describing
No,
things.
no. We have million things to do. GPE,
Then why not do them the
JE.
other way?
PES, and then TE
Do we really need total energy?
and power. Yeah, because
Well,
we need to show that energy is concept.
No.
This one plus this one plus this one has to be this one.
We're gonna solve it using conservation of energy. It's
You will see. You will see. Okay.
what?
All right.
It makes no sense to confirm your observation by using it.
First, you're gonna find the time at T1, T2, T3. Go ahead.
T1.
Good.
Okay, I mean after it falls 55 centimeters, the distance
Oh, I'll give you
is equal to
the calculator.
half AT squared. Since I have a calculator, I might as well use 9.8. So that means that the time is just the square root. Well, it's time squared is 2d over a. So that means that t is the square root of 2d over a. Okay, so we have 2 times the distance divided by the acceleration.
You're gonna use 9.8.
I just said that.
Oh.
And then we, of course, square root that. So it's about the square root of 0.112, which is about 0.335.
Hey, Dad. Isaac is giving live. I'll talk. I'll finish your live and then Daddy gonna talk to you. Okay, baby? All right, Dad loves you. Bye bye. Just a warning sign: you cannot use the same way for the next one because that's not free fall. 1 to 2 is.
I know.
Okay.
I'm doing a minor in physics.
Okay. Oh, that's right. Yeah. Sorry. Very sorry.
Okay. So how do we find the time of the third one? Well, that's simple. To make sure Dad doesn't understand it all, we're going to
please use simple harmonic.
we're going to use Lagrangian.
Dad, I don't.
So obviously, to find the Lagrangian, we have to take the kinetic energy.
Why you use Lagrangian again? What is the rationale behind it?
It uses
So Dad
energy.
doesn't understand.
It's easy and it makes sure you don't understand. So you have kinetic energy minus potential energy. Now the kinetic energy never changes. It's just half m velocity, which is the time derivative of x squared, minus the potential is not just this. It is also, well,
We're gonna check it by 2 pi square root of m over k.
what? Okay. It is also kx. So, well, technically it's not kx. You want to know why? Because you have to think about the way we're dropping the ball.
So is how many period?
No. What are you doing? So, we have the spring right here, and we have the object, and the object is going to fall on the spring, right? So we're going to say that the unstretched length of the spring is equal to, well, no, I don't think that's a good idea.
The ball is here and then whoosh!
What
So
are you
it's
doing?
just how many period?
So we're going to say that the initial height of the ball is h equals 0. Well, no. I think we're going to say that the initial ground.
Why we cannot we use the
Wait. If the ground is h equals 0.
No, not ground is x equals. Or you letting ground is. It doesn't matter. Your answer has to be correct.
Okay.
You're not gonna intimidate me by Lagrangian.
Okay. So how do we find the amount that it's been stretched? Well, this is going to be the remaining height, let's say, if the ball is over here, which means that the stretched height is going to be that 55 centimeters plus the amount of compression. So, I mean, we're not told the length of the spring, are we?
No.
Okay, so we can't use that.
No.
All right, so let's go back to using Newtonian mechanics.
Okay. Simple harmonic motion.
So to find T3, what we have to find is when, well, our acceleration, or sorry, our velocity is equal to 0. Now how do we do that? Well, the constant force downwards is going to be mg. So that's our acceleration. But it's going to change over time. Why? Because there's going to be a secret kx coming in and slowing down our object.
So when the velocity is 0, I think Fs is equal to Ks. Fs equal
That's
to
zero
Ks.
acceleration.
Huh?
That's zero acceleration. Zero acceleration is not necessarily zero velocity. In fact,
no, acceleration is not 0 at location 3.
What?
Acceleration is huge at location. There is want to go up.
Yeah, I know. That's why it doesn't stop when mg is equal to kx.
Okay.
Because that's when acceleration is equal to 0.
We'll see.
So let's find it this way. Acceleration is equal to mg minus kx. Then, by finding x of t, we can take the time derivative and get v of t. And then we can find where that's equal to 0. Okay. So acceleration is equal to mg minus kx. And we get that at the initial time, or well, 0.34 seconds. It doesn't matter at all though. What's the velocity? Well, the velocity is the acceleration times the time, which is just 0.335 multiplied by the acceleration is 9.8.
I think it's 3.28, but check.
Well, it sounds realistic enough. It's approximately a multiplication by 10. It is 3.283. So that's the velocity as soon as it collides with the spring. Okay. So now, how do we solve this? It's a differential equation. So we have, oh crap. So you have m x dot dot plus.
Can you draw the free body diagram when velocity is 0 at location 3?
Okay.
So that make sure we don't make any stupid mistake. That is Fs. Okay. And velocity, can you write velocity is 0? And acceleration is not 0.
All right.
So your FLMA makes sense. Let me see.
We're switching the directions. Okay, so now how do we solve this? Well, there's a constant solution and then a particular solution. Okay, so the homogeneous solution is just for this equation. So you get so that means that if you take the second partial derivative, if you take the second derivative with respect to time, it's just the same thing as the original function, but with a constant added, which means that we can say x is equal to e to the rt, where r is some constant number. So its double derivative, its first derivative is going to be r e to the rt, so the second one is going to be r squared. So you get r squared e to the rt is equal to minus k over m e to the rt.
This is very difficult.
Clearly, r is equal to I times the square root of k over
What is
m.
R for?
R is just some constant that we're going to plug in. So x is just e to the r is
break loose.
I times the square root of k over m t, which is just we only care about the real part of the solution, a times cosine the square root of k over m multiplied by t plus some phase shift. All right.
Okay, so what is the time?
Okay. We're gonna get to that.
Okay, all right.
Okay.
Hopefully.
I can't make any promises.
Hama. You can give up always, giving up his option. In fact, I am.
Oh, there's one piece of information that we haven't used yet. You know what it is?
Yeah. 15 centimeters, yeah, that's right. I encourage people to give up.
Okay, you should stop.
Oh, I should shut up.
So we know that we have three initial conditions. X of 0 is equal to, well, 0. X of however long it takes, so let's say t2, I don't know, is equal to negative, we're doing that in the positive direction, 0.15, and then x prime of 0 is equal to 3.28, or x dot, you can also say, and x dot of t2 is, well, 0. That's the condition. It's supposed to come to rest. So,
the hell broke loose?
We know clearly a cosine phi is equal to 0. Yeah, that sounds about right to me. This, we get a cosine rad k over m. And what does this tell us? Obviously, the amplitude can't be 0 because that would mean the spring can't oscillate. So whatever the phase shift is, it must mean that cosine is 0 at the beginning, which means the phase shift is probably just pi over 2. And of course, what's cosine of x plus pi over 2?
Cosine of x
Plus pi over 2. Are you getting it yet?
Yes.
What is it? Beep. You failed. Who wants to be a millionaire?
Yeah.
You just wrote it down.
Yeah.
It's sine x.
Oh yeah, because 90-degree shift. Are you kidding me?
So why didn't you get it?
Oh, I was just testing myself.
Okay. That's how it is now.
Are you getting the equation for?
We're getting the
period?
equation for x over time.
Oh.
Then that'll allow us
Which
to.
is 2 pi square root of m over k.
No, that's not the period. I'm finding the x over time, which will allow me to find the v over time.
Good luck.
So that means that the derivative of this is just going to be the square root of k over m, a cosine of square root of k over m t. So that means that wait. Oh, okay, crap. I'm moving. So this, of course, means that the square root of k over m multiplied by a is 3.28. And finally, we get that x dot of t2 is equal to 0. So if x dot of t2 is equal to 0, that means that the square root of k over ma multiplied by cosine of the square root of k over m t2 is finally equal to 0. So now what does that tell us? It tells us nothing. I'm just kidding. So obviously that tells us that whatever this is, it has to be a multiple of, well, cosine 0 at pi over 2. So
I thought it's square root of m over k, not k over m.
Really? Why? Oh wait, no. If the frequency is the square root of k over m, what's the period?
K of m over k.
Yeah. So that means this should be on the right track, right?
Yeah, yeah.
So we have that a sine square root of k over m t2 is equal to 0.15. And now we have that, well, cosine of the square root of k over m t2 is equal to
That's why
0.
everybody loves physics.
Now-
Everyone.
Now, of course, that means that this amplitude has to be equal to 0.15, right? And so, what does that give us for the square root of k over m?
Hmm.
21.9. And
The time?
what? No.
Or what is that?
Frequency.
Oh, frequency. Okay.
Now, of course, you can take the inverse to get a supposed period.
Is that what you got?
Yeah.
Alright, now let's see. Let's verify it. Okay, so let's verify it whether this is true.
Can I get a
So,
glass of water or a
yeah,
bottle?
one second, one second. So this is the real mass. This is the real. This one is equilibrium. This one is compress.
Definitely not equilibrium.
No, this one is equilibrium.
Uh-huh.
The location 2 is equilibrium.
Uh-huh.
Location 3 is compress.
Uh-huh.
So how many period?
What do you mean?
Uh,
Like the time from here
no,
to
no.
here?
How many period? Is it t? Is it period is?
I am pretty sure it's half t.
Half t is from here to here to here. This is half t.
Oh, wait. It goes from compressed to uncompressed to
yeah,
compressed. Then it
No,
goes
no,
back.
it doesn't. It doesn't. It doesn't.
Yeah, of course. But a normal period is crest to crest.
Normal period is crest to crest.
Yeah, so that means this is half.
No, how this is half? Let me see.
This is
Let me see. Let me
this
see.
is half of
Okay,
the way.
Look. This is compressed to equilibrium
Yeah.
is T over 4.
Oh, I get it. Okay.
So T over 4. Hold on. We're not done.
Okay, why?
Oh, no, because T is equal to 2 pi m over k. So T is 2 pi 2.6 over 1585. How much?
Okay. So I'm getting 0.0114. Now you're getting the square root of 2.6 divided by 1585.
Square root.
Okay. That's 0.04.
Then you have to divide by 4.
Okay. No, then I have to multiply by 2 pi and then divide by 4.
Yeah.
It gives me 0.0636.
That's it. Yeah. So which one is correct?
So which one is correct?
I don't know. You tell me. There is a kind of like it cannot be rounding error.
Let's settle this with a fight to the death.
Oh no, which one is correct, baby? I don't know.
Why do you multiply by 2 pi?
Oh, I cannot prove this equation. I got this equation from the textbook.
You just abracadabra'd it out of nowhere?
No. I mean, this is the simple harmonic formula. This is the simple harmonic motion formula for period. I cannot prove it. I thought you know how to prove it.
Yeah, that should be correct. I'm wondering if I have made a mistake now, because this corresponds with my formulas. So I think I just made a technical mistake.
Check where the mistake made.
Okay. Oh, by the way, I guess we should just do like a bit of a side tangent to see what T2 is. And if we get the correct answer for T2, then
T2.
the
Oh, T2 is 0.34. Okay, sure, sure,
no,
sure.
no, T2 being this.
T3.
Yeah.
T3.
Okay.
T3 should be okay. You mean T3 should be this one. Okay, so from here to here is 0.34. From
What?
here to here is
Okay.
from here to here is
Do you not remember?
0.06.
Okay, got it, got it.
And
got
you
it.
add them up.
Okay, okay, got it, got it. 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 Okay, 21.9 T2 is equal to pi over 2, right? So what's pi over? It gives me 0.071. Is that close enough?
No, you tell me. You know more math, 100 times more math than me. So I don't know. Yeah. If you are the professor, would you accept that from a student? Is this close enough to call it rounding error?
Let's calculate the percent error.
Oh, percent error is big. 0.07. Both are small numbers, so.
No, but percent error still calculates it. I think you take the difference and divide it by the original result. So just 0.007 divided by 0.064, which is about 10.9%. Yes, I multiplied by 100.
Oh, so that's not acceptable.
Is 10%?
Yeah, 10% or 5%. Where the mistake made? Can we? Either my one is wrong or your one is wrong.
Okay, okay.
Or could be both of them are wrong. That could be. I didn't get it from textbook. Textbook didn't solve this problem.
Huh.
All the textbook are stupid.
Well, that's a bit of a leap to make. Okay, let's try to solve this problem. Okay? Just starting anew.
Sure.
Why do we still not have the length? I feel like that would...
the book didn't give us that.
Okay, fine. Sure. Okay, so let's solve this using conservation of energy because this doesn't seem to be doing us any use or any work. Okay, so conservation of energy tells us that at time equals 0, kinetic energy is equal to 0. Our potential energy as well. We don't know what the length of the spring is, so we're going to say mass times g times 0.55 plus, let's call the length of the spring L. Or another proposal is to just make h equals 0 the top of the spring. That way we don't have to depend on this. So what does that make in potential? mg times 0.55. So you get 2.6, that's the mass, right?
2.6 is the mass.
9.8.55. About 14.01 joules at the start.
Oh yeah, that's.
And of course our spring potential is 0.
Yeah,
because
that's
it's
true. Yeah.
not compressed at all.
I also got 14.0.
Okay, so we know this for sure.
So I'm gonna update it. 14.
Okay.
We'll just call 14. Which one is the source of energy? GPU.
Okay. Now, at right when it's about to hit the spring,
it's also gonna 14, but it's gonna be tricky. Don't make mistake.
This is gonna
be no.
Dad, we defined h equals 0 to be the top of the spring.
No, we did not.
I defined.
Oh, you defined?
I defined it to be the top of the spring.
As long as you can give me TE49.
Otherwise, this wouldn't make any sense.
Okay,
you know why, right?
As long as you can give me TE equal to 14, I don't care.
Okay, so this is 0. This is all converted, and this is 0.
Oh no 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 no
Why are
no
you
no
making
no
that noise?
no no.
Okay, fine, fine.
All right.
I'll calculate it using the traditional method. So you get half 2.6 v squared, which is 3.283
It's
squared.
not gonna give you 14.
How do you know that?
Oh, shit. I can see it.
Why are you so sure, buddy?
It's gonna give you 1700. What?
What did you do wrong, buddy?
Okay, that's location 2. That's not location 3. Location 2 velocity is 3.283.
Yeah, that's
So,
what we've been doing.
okay, this is location 2.
Yeah,
Okay,
location 3 is what we're solving for.
okay. So
This guy's a no-no. This guy has no say.
I concede. No, not yet. Why should I concede? Okay, that's true. That's right.
This is 0. This is negative.
Yes. Oh God, that's what I was referring to. That's what I was referring to.
mg times negative 0.15. You get 2.6, 9.8, 0.15, negative 3.8.
There you go. Now we are on the same page. We are friend again. Because if you do something bad with conservation of energy, then we no longer friends.
This is obviously 14, which makes this 17.
You can just get.
We tried the conventional way and we ended up in an argument. So try the conservation of energy way.
Okay. Okay. I probably reluctantly agree.
I probably reluctantly agree.
Maybe that's what should at when you measure the time 0, it should be 55. Oh, 0. It should be 0
Why?
because you measure the time at location 1.
What?
Oh, okay, sure. I don't care. Yeah, sure. That's good.
This guy's a no-no. Oh, okay. So this is negative 9.8. This is negative 9.8. This is
It's a big number, I guess.
9.8 or negative 9.8 plus k, which is 1585.
No. Can you write the equation instead of doing this thing?
Okay.
Can you do the free body diagram?
MA is equal to minus mg plus kx. So A is minus g plus k over mx. So you get multiplied by x, which is 0.15. Honestly, it can't be that big.
How much?
I'm guessing it's at most like 20.
Not 20, baby. I guess this is like 100 or 80.
Dang, he's right. It's 91.4. Oh, wait, no. I have to subtract. I'm dumb.
Use PEMDAS.
Fremdas?
Yeah.
Fremdas?
Yeah.
Fremdas?
Yeah.
I'm so sorry.
Why so? Shall we say 82?
No.
Okay. Why? We want to be perfectionist?
We used one decimal place last time.
Okay.
And don't get messy with your sig figs.
Okay.
The chemistry revolutionaries don't like that.
Chemistry is a branch of physics. There is no chemistry. It's just a chapter of physics.
Then physics is just a chapter of math used to describe the real world. Physics is just applied math.
Physics is a chapter of
Physics,
math.
yeah, physics.
Math was discovered by physicist Sir Isaac Newton.
Ah!
Now what happened?
Yeah, and physics was discovered by a mathematician named Gauss. Does that make our score even now?
No, Gauss was born.
Gauss
was born just yesterday. I mean, Gauss was just
Gauss was like 30 years after Newton. What do you mean?
Sir Isaac Newton already laid the foundation of physics, and with Sir Isaac Newton, you can create God. Did I not make you happy?
Anyway, if Sir Isaac Newton suddenly didn't exist, Leibniz still would have invented it and around the same time.
Who?
Leibniz.
Who? That guy funeral? You know how many people?
Do you know what notation? Okay, Dad. Does this look familiar to you?
Yes, that was by Sir Isaac. Well,
If
that,
if
yeah,
Sir Isaac Newton saw you using this, he'd punch you in the face and say, "Hey, you're trying to
no, no,
respect
no.
my rivals."
The notation doesn't matter. The notation, the shot I put, it doesn't matter.
Okay, does
I take out the time. I'm still the same person with same brain, and of course a good brain.
okay, so I guess that you would still be fine with writing 1 plus 7 multiplied by
You know, typist, another typist
10
should fix it.
plus 7 to the 18th power equals
Okay, I understand. I understand.
9,010,089.
Is idea big or symbol? Is idea big or symbol big?
He still came up with the same idea, but what made
He who? Sir Isaac Newton.
Leibniz?
Who?
Leibniz.
Why? Why he had to invent calculus? He was a
What?
businessman. He was a lawyer.
Yeah,
Why
calculus.
lawyer need calculus for?
No, calculus is one of the most important things for businessmen. You don't understand?
Sir Isaac Newton stumbled upon trying to solve the
You know that's most likely apocryphal, right?
no.
Stephen Hawking could tell you something, and you'd still bend over to Sir Isaac Newton. You'd probably get on your knees and start praying if you saw him in real life.
Your middle name is Sir Isaac Newton. Your middle name is Isaac.
Did I choose my middle name?
I did. It's because Sir Isaac Newton was like important.
It was.
Without Sir Isaac Newton, there would be no physics, and thus there would be no math.
We'd probably be like 20 years behind.
Only 20 years?
Yeah.
Only 20 years?
Yeah.
Not 200 years? Because the human matters, because we have physics, we have math. That's it. Otherwise, human would be like any other animal.
Yes.
So the only reason we are valuable because we have physics.
Yeah.
And we got physics because Isaac Newton.
I don't know about that one, man.
But I do. With 100% confidence.
How long ago has it been since you took History of Science 101?
Never. Why I need to take history of science when I know history? I know the history.
It shows that you know what you're doing.
Of course. Okay.
Okay, now we find the most difficult cell in the entire chamber.
And that is fine. Yeah, that's very difficult. You gonna use different way of solving it?
No, we're not.
Oh, okay.
Okay. So,
nobody knows what is the time.
Dad, we are not going to talk about how time works.
Okay.
Okay. And we're of course going to forget that this ever existed. That wasn't anything. It was just a stray letter.
D over dx. Does Leibniz mean?
No, I mean like this. It was never a column. It never existed.
Like this, yeah.
No. There's nothing past total energy.
Okay.
No power. Nothing.
Oh, no power. Okay, sure. Oh, I see.
Okay. Right. So now, how do we find? Yes, that's the problem. So
it's not t is equal to square root 2d over g. Definitely not. You know how many student of mine wrote t is equal to square root of 2d over g? Everyone. I said no. Come on, it's not free fall. Are you out of your mind?
No, Dad, you can't say that to your students.
I did not say it, but in my mind.
Well, of course. Okay, so what is u? Riddle me this. U is just mgh or mgy of t, right?
mgyt. Okay, whatever garbage you wrote, I would say yeah, okay, no problem. Because I already know the answer, 0.06, and it has to be whatever garbage you wrote, end of the day, you have to give me 0.06. I don't know how you're going to cook your answer. you're gonna be probably like Niels Bohr and cook up something doesn't make sense, end up winning the Nobel Prize
Oh,
for that bullshit.
you can never be 1% of Niels Bohr's greatness. Oh.
I target Sir Isaac Newton. Why I want to be Niels Bohr? Why you think I have to be Niels Bohr when I can be Sir Isaac Newton? I don't dream small. Why should I dream small?
The man. Okay. This is concerning. Very
all the hell
concerning.
blows again. Good luck with you.
Very concerning.
This guy is, you know, something like like the energy of atom, hydrogen atom.
Wait, I actually forgot how to solve one of these. Isn't it an arctan function?
Oh God.
Wait. I need to look this up real quick. Just real quick.
Take a look in front of camera. So if we are like not, we are admitting that we have human limitation.
Non-linear equation. Yeah, that looks about kind of similar, except this is the one we're solving instead. Squared. Oh, that's actually quite simple. Oh, that's amazing. Okay. We're gonna pretend that never happened.
What?
That was way too embarrassing for me to talk about. Okay, so let y of t be a quadratic polynomial, at squared plus bt plus c, right?
When they're quadratic come from.
Okay, good question. Great question, in fact. Wonderful question. Amazing question. That's because you might notice, try solving for y of t in terms of this. Now, y of t is degree 2, right?
Yes.
What is y prime of t then? What degree?
Degree 3. Degree 1.
Okay, and then so what is y prime of t squared?
Degree 0. Degree 2.
Are you just like guessing a random plus 1 or minus 1?
Yeah.
You should be aiming for Niels Bohr, man. Okay, so now we plug in. So if y of t is this, y prime of t is just going to be 2at plus b. So you have that 14 minus 1/2 m times 2at plus b squared is going to be mg minus k times at squared plus bt plus c. And of course we expand this. Oh, and I guess I should plug in all of these constants. Now half m is of course just 1.3. mg minus k is a pretty big number, I'm not gonna lie. Minus k. So k over m. Oh no. Wait a second. Oh, okay. I'm not. Never mind. So that's negative 1559.
Is that the K?
No.
Oh.
Mg minus k,
Oh, I see.
which is approximately k. Okay. Now we expand this, which according to the binomial theorem, 4at squared plus 4abt plus b squared Okay, and now we finally we have to look at the constant terms, the degree 1 terms, and the degree 2 terms on each side and make sure they're equal to one another. So,
Good luck. All the hell broke loose.
the degree 0 terms are
This one could be a research paper.
no. Okay.
Not for you, but for me.
Are you implying there's lower standards for you?
Yeah, yeah. Because I cannot find anything big. I'm 45. I don't have much time left.
Come on, Dad, don't think that way. I mean, you're already working on one research paper.
Oh, yeah, sure. That is one. Okay.
Come on.
Okay, yeah.
We all know you're going to get a PhD in 3 months. Okay, so degree 2. What is that? That just minus 1.3 times 4 is minus 5.2. Oh, would you look at that? That gives us our first solution. Because if you divide by 5.2b on both sides, you get A is equal to 1559.52 divided by 5.2, which is about 300, 299.907.
That's not close to 0.06.
You should wait. The last equation we have is on the degree 2, which is minus 5.2a is equal to minus 1559a. Oh, okay, so that just gives us the same thing as this, which means that we have to get okay, here's what we have to do then. Here's what we have to do. We already know that y of 0 is equal to 0.55, yes?
0.55, yes.
Oh, yeah.
Zero.
So that means if y is a quadratic function, obviously c has to be the 0.55.
Sure.
You get that, right? Yeah. So c is 0.55, which means that 14 minus 1.3b squared is equal to negative 858 or 857.7. I don't really care. So you subtract 14 from both sides. You get negative 1.3b squared is equal to negative 872. And of course, you get the b squared is equal to 872 divided by 1.3, which is about 670 point, I don't know, 6. And then you take the square root of that. And b is 25.89, which means b is practically 26. So now we get that our function is a is 300p, is 300, b is 26, and c is 0.55. Ooh, does that even have any roots? I can't graph them on this
I
crappy
have a
calculator.
I have a font. What is that?
Wait, but this doesn't have any roots, does it? Wait, let me check. Oh, this can be plus minus, but we have to take the minus value because otherwise all of these roots are imaginary. Okay. Then we can see where the roots are.
Font. Is that font is it?
Okay, then I guess I'm using the Desmos app. Two roots. One at 0.036 and the other at 0.05. Do we just take that?
Yeah. 0.05, 0.06 are the same.
Okay.
All right. Yeah, I mean, yes, I don't know what to say.
Yeah.
All right, what is the last word? What did you learn and what we failed to learn?
What we failed to learn was nothing. I think we achieved all our objectives.
All right, so we should put the time over here then. So total time took
Trust me.
total time took 0.34.
Oh, sorry.